Okay, good afternoon, everyone. It is my great pleasure to introduce our colloquium speaker today, Professor Matthew Kupinski, and he's our local faculty here, and he has appointment with the College of Optical Sciences, the Department of Medical Imaging, and he's also an affiliate member of the program in Applied Mathematics. So he received his BS degree in physics from Trinity University in San Antonio, Texas, in '95. And then he received his PhD in 2000 from the University of Chicago. And then in the year 2000, he became a postdoc here in Professor Harry Barrett group at the University of Arizona. And he became a faculty member in optical sciences in 2002. So he is the recipient of the 2007 Mark Tetterman Award given out by the Society of Nuclear Medicine, and the 2012 recipient of the Graduate and Professional Student Council for Outstanding Mentor Award. He is an associate editor of the Journal of Medical Imaging, and currently is a conference chair of the SPIE Image Perception Conference. He has over 50 peer-reviewed publications, numerous book chapters, and he has edited a book as well. So his current and past research funding spans the NIH corporate projects on medical imaging from Canon and GE, a small company project on biometrics, and Department of Energy funding through the collaborations with Sandia National Labs and Pacific Northwest National Labs. So he has worked in diverse areas of imaging, includes X-ray, gamma ray, diffuse optical, magnetic resonance, and neutron imaging. So it is my great pleasure to introduce him today, and please join me to welcome Matt Kupinski.
Thank you much. I'm going to talk today about image science in medical and security applications. And what I'm going to try to do is give you a flavor of the type of work that we do. And I will talk specifically about 3 different and fairly broad applications of our ideas. But the first thing I want to do is really sort of define what image science is for those of you who don't know. Image science is the multidisciplinary field. It's concerned with the generation, collection, duplication, analysis, modification, and visualization of images. I know this is true because Wikipedia says it's true. But basically, the overall goal is to generate images that are more scientifically and or medically useful. So our goal is to generate images that are more useful for the task in which they're generated. So we try to take a broad view of imaging. That is, we need to consider all aspects of the imaging chain. That is, the objects, that is, what's being imaged, the patient population, for example, that's being imaged. We have to consider the imaging system and all the physics that associated with the probing the patient with radiation. We have to consider the image data and the noise statistics that are present in the image data, the post-processing that goes on, and finally the image analysis where somebody takes that image data and produces some sort of decision. So, as I was just saying, all aspects of the imaging chain need to be understood and accounted for when performing system analysis and system design. And what this leads to is an idea of image quality that is task-based. So instead of looking at analyzing the system itself, if we take sort of a more full viewpoint of the process, then we have to consider what's called task-based assessment. So in order to analyze these imaging systems, we have to consider the task. That is, why are we generating these images? What are the images to be used for? We have to consider who is performing this task, who or what is performing this task. We have to know something about the objects that you're imaging, the patient population or the population of objects that go into your system. And the overall goal is to measure the ability of this observer to perform this task on this class of objects. So that's essentially what we're talking about. What are we not talking about? It gets loud. we're not talking about things like MTF, noise power spectrum, resolution, contrast to noise ratio, etc. Which is not to say that these things aren't important. They are important, but they do not necessarily relate or correlate with task performance. That is, why are you generating the images in the first place? And I always like to give a cartoon example using contrast to noise ratio, because this is one you see in medical imaging all the time, even though it's been debunked for years. But if you just have a sort of very stylized task where I have to detect that simple pillbox signal in a noisy background, and I am plotting here, all the various rows have equal contrast to noise ratio, so 2, 1, half, and a quarter. But the various columns, all I've done is change the pixel size. And what you find here is that, sure enough, if you look, say, at, let's look at this row here, when the contrast to noise ratio is 1 and you have lots of pixels, I can see that signal very well. When I go to a coarser pixel size, coarser pixels, I should say, the signal effectively disappears. And it's even more visible in some of the lower CNRs. So contrast to noise ratio, while it's quantitative, it doesn't necessarily and doesn't actually specifically correlate with how well we can see signals or how well you can perform this particular task. So relevant tasks that I'll be talking about, signal detection, that's kind of the one I just talked about, taking an image and trying to determine whether there's a signal present in that image or not. Signal estimation, so given that a signal is present, that may not be all you need to know. You have to know where it's located, the size of that signal, et cetera, et cetera. And combined tasks, which combine have a signal detection and an estimation component to them, which is really the sort of more realistic tasks. If you told somebody there's a signal in that image that's not very satisfying, they want to know where it is, or maybe what type of signal it is. Those are the tasks we'll be dealing with. The observers that we often consider are things like humans. We do consider human observers, but more often than not these days we're considering more computer algorithms or model observers, as we call them, and sometimes even ideal observers. These are mathematically ideal observers. They're optimal in some well-defined sense. So if I put all this together, what we find is the following. We find that image quality is a statistical concept. That is, I can't compute image quality by one or even a couple images. I generally need lots of images. And so this is an example here where, let's say we're doing a signal detection task. These are, I think, cardiac images of maybe a rat. And we're maybe looking for a defect. There you can see a little defect here. So we have a bunch of images, the ellipses here, that do not have the signal. We have a bunch of images that do have the signal. They are all input to an observer who looks at those images and makes a decision. That decision may be, in this particular case, producing a decision variable, which you can think of as sort of their confidence that the signal is present. So they're producing a number which indicates how confident they are that there's a signal in that image. And of course, there's two distributions here because there's two types of images. There's the images that have this negative signal, this depression, and there's images that don't have that signal. And so we end up with two distributions here. Now, you have to make a decision. So a decision is generally made by setting a threshold. Everything to the right of this threshold, we say, is you call a signal present. Everything to the left, let's say, is signal absent. And using this threshold, we can now define some performance metrics. That is, for example, the true positive fraction is the area under this signal present distribution to the right of the threshold. The false positive fraction is the area under this negative distribution to the right of that same threshold. And these are probabilistic quantities. The true positive fraction tells you how often, or what's the percentage of time that you correctly classify signal present images. The false positive fraction tells you the fraction of times that you misclassify normal images. And I can plot these two fractions in what's called an ROC space. So here's the false positive fraction, the true positive fraction. I get 1 point in what's called ROC space, receiver operator characteristic space. It's from the radar literature in the 50s. That's for one particular threshold. This observer produced essentially distributions or lots of different values for this decision variable. And so as you can imagine, I can change that threshold If I lower the threshold, my true positive fraction goes up. I more often correctly classify the abnormal images, but correspondingly my false positive fraction also goes up, which is a negative thing. I'm more often misclassifying normal images. And if you can, you can see what the end game is here, we're going to sweep out from plus and minus infinity and generate what's called an ROC curve, which is basically my TPF and FPF, my true positive fraction and false positive fraction, for all possible thresholds of this decision variable. Now, I'm bringing this up here because this is sort of the figure of merit that we'll see later on throughout this talk, and so it's useful to have sort of this definition. It's important to keep in mind that what we're trying to do is maximize the true positive fraction and minimize the false positive fraction. So we want this curve to go as up and far to the upper left corner as we possibly can. Again, it's generated from this test statistic data. If I had a different observer or a different task or a different imaging system, I might get a second observer. And the second observer, as you can see, the distributions are more separated than observer 1. And I get a better ROC curve, one that's more up and to the left more towards the upper left corner. And what we generally do is we generally use the area under this curve as a summary figure of merit, because we don't want to deal with two types of figures of merit. And so the area under this curve is a task-based figure of merit. It has a dynamic range that ranges from the best value, which is a value of 1, an ROC curve that goes all the way up to the 0, 1 point, and then all the way over. And the worst possible performance, I won't talk about it here much, but the worst possible performance has an area of a half. The guessing observer goes from 0, 0 to 1, 1 in a straight line. So this is just sort of the setup for what I'll be talking about in some of the applications here in just a moment. But just keep in mind, this is what we'll consider a task-based metric of image quality. The observer is performing the task, making decisions. We are assessing how well that observer is making those decisions using the image data, using the imaging system, and using whatever processing algorithms. Okay, so on to the applications I'm going to talk about. I'm going to talk about 3 applications in this talk. The first is the role of image quality in dose reduction for CT imaging. I'll get more into these in just a second. The second is adaptive preclinical imaging. And the last one is not medically related at all. The last one is the role of imaging in what's called treaty verification. And if I were to put labels on all of these things, I would say that the first one is a clinical application. These are imaging systems we'll be talking about in this first application that are used on patients, on actual humans. The second one is a small animal application. It's a preclinical imaging. It's generally we're imaging small animals. And the last one is, as I'll call it for lack of a better term, it's a homeland security application. It's not medically related at all, but it is image data, and there is a well-defined task. Okay, so on to this first one, the role of image quality in dose reduction for CT. For those of you who don't know what CT is, some people call it a CAT scan, but basically you're probing the body with at many angles using ionizing X-rays. So we are, instead of producing a planar image, like you get a chest radiograph or imaging a broken bone, with CT you're imaging the patient at numerous angles surrounding their body, and often as they traverse through the bore of this system. And the overall goal, usually the overall goal people consider, is to reconstruct some sort of attenuation map or average attenuation map of the body. And when you do that, CT images do produce very nice, beautiful images. This is an axial slice through a patient. You can see the liver, probably the stomach, the spine. You can even see the ribs crossing here. You can see the bed down here. And if you look closely, I'm not sure it's showing up here as well, but you can see sort of depressions in the liver area and things like that. Now, one of the problems is that CT, they produce exquisite images, very high-resolution images, fairly good contrast, soft tissue contrast, but they're using patients are imaged using ionizing X-rays. And in a lot of cases, many patients receive multiple CT scans in a relatively short time frame. And especially if you have a cancer diagnosis, you might get a PET CT scan, every few months to see if the cancer is recurring. There is a CT component of that scan. And while the benefits of CT generally far outweigh the risks, the absorbed dose should be minimized as much as possible to mitigate any carcinogenic or other deleterious effects. So, I'm not here to say that CT is necessarily dangerous, but whenever possible, we should try to minimize the exposure or the dose delivered to the patient. And this is especially true when dealing with children getting, childhood cancers, and they're getting CT scans. They may be getting a substantial dose that may affect them later on in life. Now, the thing that we specifically looked at was the role of image reconstruction in this dose reduction. So image reconstruction is sort of the processing aspect of the chain that I had earlier. So we have this raw data that comes from the imaging system. You shoot these x-rays all around the patient. You take all your measurements. Those are, for lack of a better term, projection images through the patient. You want to now take that information and reconstruct what the distribution of attenuation looks like in that patient. The general conventional way of doing that, the thing that's been used for decades, is something called filtered back projection. It's a mathematical tomography method. It's essentially geometry based. It is very fast. It doesn't take any time to do, but it doesn't really account for the complicated physics and the complicated statistics that may be present in your image data. And so people have been working on, for a number of years, applying statistical methods or statistical reconstruction techniques to CT. And the advantage of having a statistical method is that you can account for all of the measurement noise. So all the noise present in this data, you can build that into your model. You can also very accurately model a lot of the physics processes that go from, model the physics processes, modeling the x-rays going through the patient, hitting the detector, and all of those various interactions. So, statistical reconstructions may provide quite a bit of benefit, and our goal was to see if that benefit's actually realized. Now, I say we're looking at dose reduction, and I'm talking about image reconstruction. This is a little bit of a, it might seem like a little bit of a red herring. The data has already been generated. The patient's already been dosed. So what are we trying to do here? Well, our goal was to test whether, using statistical reconstruction methods, can we maintain image quality while lowering the dose to the patient. So using statistical methods, can we lower the dose and get an image quality, a task-based measure of image quality that's equivalent to what they had with a high dose, and using the conventional filtered back projection. What I'm presenting now is the work of Dr. Andy Tseng. He's right there. This is him visiting GE. He spent a number of summers at GE using one of their systems, GE Discovery 750 HD, to gather all the data for these studies. And the work I'm presenting is his. He is Dr. Tseng because he just defended Monday. And let me just show you a couple images, what things actually look like. So these are two reconstructions from the same data sets, one using the conventional filtered back projection, one using a statistical reconstruction method that, again, it's really, this looks quite a bit better, and as I'll show you, it's going to be quite a bit better, but it's really should be somewhat obvious. The statistical reconstruction technique is really accounting for the physics and the statistics, while filtered back projection is a mathematical technique, and there's lots of approximations. And just those were two sagittal slices. Let me just show you a couple axial slices. Again, the filtered back projection, it looks to be a lot noisier. The statistical reconstruction methods seem a whole lot smoother. Now, I say that, but in a lot of cases, people would leave this and say that's enough. But what we are really trying to do is be quantitative about it and say, really, how much better is this statistical reconstruction compared to the filtered back projection. Okay. So let's talk about the task. The task here was a simplified task, and I'll talk about some of the limitations of that in just a bit. But our goal was to detect and locate low contrast signals Here are those low contrast signals. There's actually 4 of them. This is a phantom, something we put in the imaging system just to gather data. You can't really do these types of studies with volunteers since you are delivering ionizing radiation. This is not an example image. This is an average of something like 500 images. So these are, in fact, very weak signals. You can see them here, but in actuality, they're very difficult to see. This is a realization of what 3 images might look like. The one on the left here actually has a signal present. The next 2 do not have a signal. And so part of what Andy did in his work was he was at GE. He was acquiring hundreds of images of phantoms like this with low contrast signals. And these are very low contrast signals. They're very, as you can kind of see here, the signals are quite difficult to detect. So that's the task. Our task is to find these low contrast signals. What is our observer? I don't want to get into the mathematical details, but our observer was designed to simulate the frequency and orientation selective channels of the human visual system. This was work done by a lot of people, but we based a lot of what we did on Craig Abbey's work. He was a former person here at the U of A in the program in applied mathematics. And so these 2 guys, I think it's Hubel and Wiesel, did some work for which they won the Nobel Prize. Studying mammalian visual systems, and noted that one of the first things that happens in our visual system is that we have these sort of frequency and orientation selective channels. So we are processing image data as it comes in using these sorts of channels. And so we and others have used that to model how humans would perform in these types of signal detection tasks. So we can generate frequency and orientation selective channels. We can operate the image with these channels. And once you have these channel outputs, we do optimal processing of the channel outputs using essentially ideal observers. And so this is all based on the idea of how the human visual system evolves. We have these, essentially have natural compression in our visual system, these orientation and selective channels, and once we do that compression, we optimally process the channel outputs that result in data. And that's what we implemented here, again, based on the work of a lot of other people. So let me just show you some example results. These are ROC curves, just like I showed you before, but now we're doing a comparison. Again, this is a plot of the true positive fraction, the fraction of times you correctly find that signal in images that have the signal. And this is the false positive fraction, the fraction of times you misclassify images that don't have the signal. Again, we want it to be towards this upper left corner. There's 3 curves here. Let me just show this first one here is in yellow. This yellow curve is the filtered back projection result at a very high dose or high exposure. So the tube current was turned up. You're providing quite a few X-rays. You're getting good image data, low noise image data, and doing the conventional filtered back projection. When we lower the dose but use filtered back projection, we get this red curve. So the observer's performance drops fairly substantially from the yellow curve to the red curve. But when we use that same data but use a statistical reconstruction method, our performance is shown in the light blue curve here, which is nearly equal to, so let's say, for all intents and purposes, it's equivalent to the performance we got with filtered back projection at high dose. So this is a demonstration that, sure enough, using the statistical reconstruction method, we can lower the dose and achieve an image quality that's equivalent to what we saw with filtered back projection at a much higher dose. Now, that's an example result. That's for a task of doing just signal detection. Andy did a lot more studies where he did more complicated tasks, signal detection and localization, estimation tasks, things like that. I won't go into all those details, but I'll sort of summarize some of the things he found. And by simply using statistical reconstruction, it allows us to reduce patient dose anywhere from 58 to 80%. Now, I want you to see those numbers and kind of be, impressed. That sounds great. It is great. Those claims of dose reduction were included in an FDA Food and Drug Administration 510K application that was approved in 2010. And essentially, the methods we used were sort of derivatives of of methods that the FDA and these companies work together to sort of form in order to validate these low-dose claims. But it should be noted that the actual claims maybe aren't this high. So, we're saying 50 to 80% dose reduction. In actuality, it may not be that high. Why is that? Well, if I go back to that imaging chain that I showed you earlier, where we have the object, the imaging system, all this stuff, we have the system, we have the data, we have the post-processing, we have the image analysis. We did not consider anything about the random objects. So we had a phantom that we were imaging. A phantom is a lot simpler than imaging, a room full of people and trying to do similar tasks. So in actuality, the claims might not be as high, but our initial results are showing that, sure enough, using iterative reconstruction methods, we can probably get a dose reduction, or we can use a dose reduction, implement a dose reduction. Okay. On to the next application. The next application is adaptive preclinical imaging. And so in the first application, I said one of the things we didn't consider was the random objects. In this application, the primary consideration is really the random objects. And so we're sort of shifting focus from something that ignored one aspect of it on purpose to something that's trying to account for the patient variability in a very direct manner. So what is adaptive imaging? Well, adaptive imaging is something you see every day. It's imaging where the data acquisition protocol or the hardware configuration is autonomously modified in response to information received on a particular subject. So basically all this means is that it's a smart imaging system. It's an imaging system that when you point it at something, it recognizes some aspect of that, of what it is you're imaging, and modifies the system accordingly. What adaptive imaging is not, we're not considering adaptive post-processing or post-acquisition processing. So, adaptive filtering techniques and things like that, we're not really considering that. Once you have the data, what you do after that is processing and perform the task. We're not including pre-acquisition modification of the system or the protocol. So if you see that you have a big patient coming in and adjust the system accordingly, that's not adaptive, that's adjustable. We're not including human intervention during acquisition. It has to be autonomous. And the desire here is to be optimal for the current patient or the scene being imaged, and not for a broad class of objects. And so really the goal here is patient-specific imaging or object-specific imaging. And now, there's lots of examples of adaptive imaging. Anyone with a camera in their phone, that's an adaptive system. People in astronomy have been using adaptive optics for decades, or at least a decade. And there's other medical imaging examples as well. So in your digital camera, you have autofocus, auto exposure, auto zoom, face recognition, histogram balancing, adaptive illumination. All these things are done automatically just by the camera analyzing the scene at which you're pointing the system at. Here's an example of doing face recognition where they've identified 3 faces. And I always enjoy this slide because the green one, according to the website, is the main face. I don't know why Dad gets the main face. I guess he's in the middle, but he's the main face. So digital cameras are adaptive systems already. As I said, in astronomy, it's done all the time. If you take a conventional telescope and image a distant star and do a long exposure, you're going to get a sort of blurry point because the atmospheric turbulence is going to affect your system pretty dramatically. If you take short exposure images, you're essentially freezing one instance of the turbulence. And so you get nice tight spots, but all those short-range exposures, you get lots of those nice tight spots. And if you use adaptive optics, you can correct for the atmospheric turbulence, adjust the wavefront, do wavefront corrections, and you'll get a nice tight diffraction-limited spot. Again, this is not my work. I'm copying from the internet somewhere. And these are how these things generally work. You have the light from the telescope. You have an adaptive mirror. the light from the telescope is split. Some of it goes to the science camera, and others go to a wavefront sensor, which controls this adaptive mirror to try to correct for the turbulence in the atmosphere. Adaptive imaging has also been used extensively in CT, the application I was just talking about. All modern CT systems have what's called automatic exposure control. So when you are imaging a patient, you do not provide the same exposure or the same, I'll say exposure, I can't say dose. You don't provide the same exposure for all regions of the body. There are some regions that are quite thin. Here the neck is quite thin. There are some regions that are quite thicker, the torso, and the head is in between. And so you modulate the tube current as the patient goes through the system, and provide the way the systems currently work is they provide less exposure in the thin regions and more exposure in the thick regions. Whether that's optimal or not is questionable, but that's currently what they do. They are adaptive. They adapt to the current patient being imaged. And so, depending on the size of a patient, the tube current modulation will be different every time a different patient goes through the scanner. Now, what I want to talk about is some applications of adaptive imaging developed at the Center for Gamma Ray Imaging, for which I'm a part of. And at CGRI, I guess I should have done a small animal example, but at CGRI we're doing gamma ray imaging. So unlike the CT example where I showed earlier, where you're trying to generate an attenuation map of the body, in gamma ray imaging you inject a radio tracer, a gamma emitting, in this case a gamma emitting radio tracer into the patient. It is designed to follow various physiological pathways and attach itself to things like bone or fast-growing tumors or things like that. And then you image the gamma emissions from this patient using a series of cameras surrounding the patient, or using one camera circling the patient. And so this is what's called functional imaging. You don't get a nice, pretty image of the anatomy. You get an image of where this radio tracer was distributed in the body. It's very useful for it's used all the time. SPECT is used all the time in cardiac studies and cancer studies as well. Now, as you can imagine, we are imaging gamma rays, so these are generally high-energy photons. So we are not using lenses. We're not using conventional optics. Our optics are generally made of lead. Things like pinholes, things like collimators, parallel hole collimators. And in a lot of situations, we use multiple pinholes. So why use multiple pinholes? Well, you increase the sensitivity. One pinhole doesn't allow a lot of light through. Two pinholes, effectively doubles the amount of light that you let through. The negative of adding multiple pinholes is you may get overlapping projections. And so, what I'll talk about here in a minute is essentially pinhole and multiple pinhole type systems. Now, in the history of this, I guess I wouldn't. In my mind, it started with some work that a former student, Jacob Hesterman, I don't have his name on here, did a long time ago. But he developed a very simple imaging system. These three things here are cameras. There's a fourth camera that's removed. This is essentially lead and tungsten shielding material. The animal goes right in the middle. And there are various plates that we can insert into this object, into this aperture, I should say. And these plates can have various pinhole configurations. So you see one pinhole right there. This plate here might have 3 or 4 pinholes. And we designed this system as sort of a test bed for image quality. So what we wanted to do a test was whether when we measure image quality in the computer, in silico, as some people would say, does that translate to what we actually observe when we take data with a real system. And so, Jacob developed lots of different pinhole plates that he could insert into this thing. He developed a phantom, an object model that was random. It was different every time he took an image. He had a well-defined task. It was a signal detection task. And he worked on the problem of how do I choose the optimal configuration of pinholes. And somewhat unsurprisingly, he found that the optimal answer depends. It depends on lots of things. So I'm not going to get into what these configurations are, but here's essentially 4 different aperture configurations, 4 different pinhole configurations. This is a measure of observer performance. Think of this as being related to the area under that ROC curve. And what he's plotting, and here higher numbers are better. And what he's plotting here is observer performance as a function of the size of the signal we're trying to detect. And sure enough, when you have small signals, aperture 3 is the optimal. But when you have large signals, aperture 3 suddenly becomes not only suboptimal, but the sort of the worst choice of the 4. And so the optimal system depends on what it is you're imaging. It depends on what it is you're trying to do with the images. And so it's, when you end up optimizing the system in the presence of object variability, in the presence of the random anatomy in the patients or in the mice, you end up with sort of an answer that is a trade-off between all the possible objects. You end up with something that's made a lot of sacrifices and is not necessarily optimal for one particular patient. So, in this example, it's not an adaptive example, but in this example of m³r, there is not a single optimal solution. The system configuration depends heavily on the task. It also depends on the objects. Now, I've tried to minimize equations in this talk. I'm going to have 2. This is the first one. But the thing I want to just drill home here is that this is a representation of imaging, a stylized representation of imaging. F here is the object that you're imaging. It's the patient in the system, the animal in the system. N here is the detector noise. It's written as additive, but it doesn't have to be. H is the imaging operator. All the physics go into this H operator here. And G is the data that comes out of the system. And the important thing to keep in mind here is that everyone knows the noise is random. It's noise. But the object is also random. And so dealing with this random object poses lots of problems. So traditionally, we have had to use objects that represent the true patient population or simulated objects that have similar statistical properties. But what we're really often dealing with, or conventionally dealing with, is what's the probability density of the patient population being imaged. It's a hard question to answer, but that's often what people are considering. So what is PRFF? Well, it's the broad distribution of all possible patients that are to be imaged. It's needed for task-based assessment, but how do you optimize the image quality for one particular patient that's drawn from this broad distribution? And so let's now sort of pose this in an adaptive imaging construct. And an adaptive imaging construct, I'll consider the simplest one, which is acquire some scout data and adjust the system based on that scout data. So imagine a system that turns on for a few seconds, takes some initial measurements, processes those measurements, and then adjusts the imaging system to be optimal based on that data. And so in this particular situation, the imaging operator now becomes a function of the scout data. So we're adjusting the imaging system based on these scout measurements. And the key point, the sort of aha moment, for lack of a better term, was instead of trying to optimize the system for all possible patients, so that is, instead of trying to come up with a system that worked for all the broad class of all objects that would go into this system, we're going to instead try to understand this conditional distribution. And this conditional distribution is the distribution of objects that are consistent with the scout data that we actually observed. So, what does the scout data? Oh, I'm sorry. In addition, what does the scout data tell us about the relevant task? I won't talk about that. But this is the distribution we're trying to understand. What's the distribution of the image of the objects that's consistent with our initial measurements? And the sort of graphic picture of how this looks is if you consider a generic f-axis. This is, of course, infinite dimensional in reality. You have this distribution of the objects that's very broad. There's a broad class of people or subjects that would be put through this imaging system. But once you take a set of initial measurements, you now have a much narrower distribution, the distribution of objects that are consistent with your initial measurements. It's not a delta function. If it was a delta function, you wouldn't need to continue imaging. The scout data would tell you everything. But it is a narrower distribution. If I put in a new patient and generated new scout data, I would get a different posterior distribution, a different distribution of the objects consistent with that new scout data. So back to these key points. We're going to measure scout data. We're going to use this posterior distribution as a sampling distribution to generate objects that are consistent with the data. And we're going to assess and optimize task performance using these objects. And this is akin to something people in medical imaging are talking quite a bit about. It's akin to something called a virtual clinical trial. It's basically, we're going to sample objects, sample patients that are consistent with the scout data, image them in simulation, assess their performance, and use those results to modify the system based on this scout data. So this was done in a very simplistic way by a master's student a few years back, Tara Trumbull. She used, this was done in simulation. I'm going to show you the realization of some of these systems in just a minute. But she used this sort of, I will call it an accurate, I don't want to call it accurate, but it's a very complicated object model of a mouse. You can change all the organs, move them around, make the mouse bigger and smaller. She generated 16 projections of this mouse for simulating 16 cameras surrounding the animal. That was the image data that was used, but this was a system that she was modeling that she could modify the pinhole configuration. And her goal was to use this patient population, to use, initial measurements, the initial scout measurements, to test these various configurations of the system to see if she could maximize task performance. And for her task, she didn't consider signal detection. She considered signal estimation. So often in animal imaging, we know there's a tumor present. We put it there. The goal is to see if that tumor is shrinking or growing. And so her goal was she dealt mainly with an estimation task, estimating the activity of the tracer within a certain region. And sure enough, she was able to rank order these systems based on performance. Here, lower numbers are better. And she had 15 configurations. And she was able to find, sure enough, there's a couple optimal configurations using this type of, it's a simplified version of this type of analysis. Figuring out what that posterior distribution is, sampling from it, and assessing task performance to try to adapt the system. Now, this is all culminated in a beautiful system that is almost complete. It's the AdaptiSPECT system. This is the work of Cecile Shea, also Dr. Cecile Shea. She just defended last week, I think. This is a preclinical system. It looks like I'll call it a mess of wires. It looks very complicated here. It doesn't have its skin on it. But let me show you, sort of talk you through how this works. This is a system that will have 16 cameras. These black boxes here are the gamma ray cameras, the gamma cameras. The animal goes in the middle here, into the bore here in the middle. This aperture here, aperture here is shown here. It's a pinhole aperture. And so we are generating pinhole, or sometimes multiple pinhole projections of this animal on the 16 cameras surrounding it. You can see a ring of 8 here. Behind this metal plate, there's another ring of 8 cameras on the other side. Now, the nice thing about this system, and it's really it's an amazing system. If you get a chance to see it, you should. Is this aperture moves in and out. It's under computer control. It can move in and out. And so if you move to this inner ring here, you have very small pinholes that are very close to the animal. You get lots of magnification. If you move this aperture further out, you're into this mid-magnification region. And if you move it out further, you're in this low magnification, possibly even a minification situation. These cameras, so you can move this aperture in and out to select various bore sizes, essentially various magnifications. You can also move each of these cameras in and out, and they're all under independent computer control, and it's all very precise with the electronics that were designed in-house and everything. And furthermore, when you're at these mid-magnification and low magnification settings, you can actually select from a single pinhole configuration or a 5-pinhole configuration automatically using shutters. So all these little pinwheels here, they're actually a shutter system that I'll show you in a second that open and close to allow either a single pinhole configuration or a 5-pinhole configuration. All of this is under independent computer control, so you can open up one of these and leave all the others closed. and so forth and so on. So you have lots of degrees of freedom. Each of these cameras can move in and out independently. This pinhole aperture has essentially 5 settings. 1 for the high mag, 2 for the mid mag, and 2 for the low mag. As I said, all the cameras move in and out, and of course we can move the animal in and out of the system as well. Let me just sort of show you some of the design that had to go into this. So again, this is all Cecile's work. She's Lars Furenlid's student. This is that high mag aperture. I believe it's tungsten panels here that were sort of configured in a barrel configuration, done in such a way that there's no light leakage. There's no straight line that you can draw through these septa. You can see the pinholes here. Those are, I think, 0.6 millimeter pinholes. Again, surrounding this thing, there's 1 pinhole for each camera, so you can sort of see the configuration of the cameras. There's 8 in this ring, and there's 8 in this ring. As I said, the mid and low magnification apertures have a shutter that can turn on and off. Here's the shutter in its single pinhole configuration. So you have these little tungsten blocks that are blocking 4 pinholes here. You use this pneumatic lever here to push the piston, and it opens up to a 5 pinhole configuration. And when the piston lets go of pressure, the spring pulls it back. And it's a very fast operation. You can open and close things. This is done with plastic, but you get the idea. You can open and close things at a very fast rate if needed. I'll mute it here. As I mentioned, the cameras move in and out. So if you look closely, you can see that this camera is moving in and out. All of this is done with sort of very, not only precise stages, but sort of precision methods for confirming the position of these cameras so that we know sort of precisely where they are. And Cecile has taken data with this system and generated reconstructions. This is a simple phantom, but just to sort of illustrate how this system works. It's a sort of a resolution phantom, and it's hard to see here. I can see it on the computer quite well, but these smallest rods are, in fact, distinguishable in this recon. Now, I just want to go one last point on this system. Here, I'll go to the first picture. I think it's kind of a, I don't know. So, as I mentioned, most of the system was done in-house. All of the design and configuration of the system was done in-house. All the electronic boards were designed and stuffed by people in the Center for Gamma Ray Imaging. This aperture was designed and built mostly in local machine shops, I believe. The only thing we didn't have a whole lot of control over were these 16 cameras, and wouldn't you know, those are the things that are giving us the most trouble. So this system is, we're having a camera issue right now, trying to get up to a full set of 16 fully operational cameras. Okay, one last point on this before I switch topics and talk about something completely different. I said, I talked a lot about that posterior distribution, the distribution of objects consistent with the SCOUT data. You still need this. You still need this because if we're to assess the overall performance of the system, we have to use this to sample the objects that we're imaging. So even though we use that posterior distribution to measure image quality in a global sense, we have to use that distribution. We can't ignore it. Okay, I want to talk about one last application. I had a clinical application. I had a small animal application. The last one, as I said, is more of a homeland security application, and it's the role of imaging in treaty verification. So this is something quite different, as Monty Python would say, and now for something completely different. This is a project that's funded by the Department of Energy, and it's a collaboration of 3 places, Pacific Northwest National Labs, or Lab, Sandia National Labs, and of course us here at the University of Arizona. And this is a project on arms control. So I'm not doing medical imaging anymore. I've switched hats completely, and it's more of an arms control application. It is an arms control application. And the way to think about this is you hear about treaties, nuclear disarmament treaties. And a big problem that occurs is you have this treaty. You say you're going to disarm these warheads, get rid of these delivery systems. How do you verify that that's actually taking place? And so in the Cold War, the focus was on launchers as the treaty-limited items. And that was because in the Cold War, there were lots of warheads. So it didn't really matter if you got rid of so many warheads. What mattered was your ability to launch those warheads. And so during the Cold War era, the launchers were the treaty-accountable item. And launchers are easy to count. You can look at a launcher and say, yes, that's a launcher. You can see if it's been dismantled quite easily. And it, as I mentioned, the exact number of warheads doesn't really matter when you have a large number of them. But we're getting to an era where we're trying to really reduce the number of warheads to a very small number. In fact, in 2009, Obama stated that the goal is to have 0 warheads. And so there's an emerging focus on counting warheads and not just launchers. So when a warhead, something that the head of a nuclear bomb, when it's the treaty-limited item, is it possible to have sort of cradle-to-grave accounting of these things? That's an important aspect because you don't want to lose track. You don't want to lose a warhead. You don't want somebody selling it. And warhead counting requires that an item be determined to be as defined, or to be a defined warhead. And there's a lot of security challenges with this, as I'll mention. And just to sort of give you an idea, the START treaty, I think it was signed in 2011. I don't remember when it or if it's gone into effect. It limits the U.S. to 1550 warheads and 700 delivery systems. So already our treaties are now using warheads as one of the things we're trying to limit and reduce. And so what's the issue? Well, the best way to explain the issue is to have a cartoon. So here's the issue. We have 2 nations, let's say us and Russia. We have a host and a monitor, and of course, at some point they'll switch roles, and they'll be the host and we'll be the monitor. And the host invites the monitor over to come over and inspect their warheads. And so the monitor walks over, flies over, I guess. And the host says, here is my disarmed warhead. It's in a barrel. Please go ahead and verify that it's a disarmed warhead. But whatever you do, don't open the barrel and don't gather too much information on what's inside the barrel because if you did that, you would know how to make bombs better. So, and they have the similar concerns with us. They don't want to inform us how they make their bombs. We don't want to inform them how we make our bombs. So determine that this is a disarmed warhead without looking inside of it and without gathering too much information. And early attempts at doing this, sort of research efforts, had these things called trusted processors. Why is it a trusted processor? Well, it's a processor that's basically sealed, welded shut, and you can't really get into it. But there's still inputs to this processor, and if you could tap into those inputs, you can have trouble. So the goal is to come up with a way of verifying a treaty-accountable item, a disarmed warhead, for example, but do so in such a way that you reveal no information about what's inside. And hopefully do that, and everyone's happy, and the 2 host and monitor have a beer, and everyone's happy. So all this discussion, I have to start talking about what's called what the DOE calls an information barrier. Information barriers are a big problem. That trusted processor was an attempt at coming up with an information barrier. So an information barrier, when you have sensitive information and you have somebody visiting from a foreign country, you want to hide that information. They take very seriously how they hide that information. Information barriers are costly, expensive, and they slow everything down. And imaging, as you might suspect, it seems suboptimal in terms of an information barrier. Imaging systems generate beautiful images of, a tomographic system could generate a beautiful image of what's inside that barrel. And so that would be great if you want to verify that it's a disarmed warhead. But if you want to hide information, that image is sensitive information and can't be used. So as I said, they can generate beautiful images of the contents of a barrel, but they provide both spatial and they can also provide both spatial and spectral information, as we'll talk about in a second. But you don't want these beautiful images transferring hands. And so let me sort of set up how this might work. So in what's called they call it a template matching approach. This is sort of the classic way they do it. There is a trusted object. There is a system of measurement. I put here an imaging system. And there's the data from that system, which I've shown here as a projection image. This is a trusted object. Both parties agree that this is, however they do that, through their treaty process. They agree that this is a treaty accountable item. There is the object to be tested. It goes through the same imaging system, produces data. They compare the trusted object data to the tested image data, and they come up with a red light or a green light. That is this tested object like the trusted object, or is it not? Green light or red light. Now, everything in red here, the way it's posed, has to be behind an information barrier. Clearly, the objects have to be behind an information barrier. They're in a barrel. That's the information barrier, essentially. The image data has to be behind an information barrier because I can use this data to reconstruct what the object is. And even the imaging system, you can't have access to it while the data are being acquired. And so, you have access before and after, but not while the images are being acquired. And so there's lots of red squares and lots of yellow squares. There's only really one green square, which is the answer, which can be shared among everyone. And so our goal in this project is to push back on the red and try to turn the red green as much as possible. And so what we're trying to do, and I'll talk more about how we do this in a second, is these things always have to be behind an information barrier. People have done a lot of work on those barrels and how to make sure they're not tampered with. But we're trying to make it so that you can generate data that is well, it may be sensitive, but it's not going to be stored. And we're going to have observer models here that are going to try to be as insensitive, and by insensitive I mean have the least amount of secure information, but still be able to make a decision. So our overall goal is to try to make as many of these boxes green as we possibly can. Oh, and I'll mention this here just because well, this is by the way, this is the work of Chris McGann, who's been working on this project for a few years. One of the things we're going to do is we're not going to generate an image. We're not going to aggregate data. The data are not aggregated. And my student said, think Snapchat. And I actually don't know what Snapchat is. So if that works for some of you, that's great. We have to, in this problem, we have to deal with what we'll call toy problems. When you think of a toy problem, you usually think of a problem that's quite easy. In actuality, we've been told that these toy problems may be harder than the actual problem. And what has been developed is what are called the Idaho inspection objects. They're developed at Idaho National Lab. And they are a set of objects. There's sort of plates that you can construct, sort of like nuclear Legos that you build up. And we're dealing with two of them. This one is a plutonium source surrounded by, I can't remember which one's which, but one of them is surrounded by highly enriched uranium. The other one's surrounded by depleted uranium. There's some aluminum shielding or aluminum materials around everything. And these are sources that are emitting gamma rays and neutrons. And so we are not doing active imaging. We're not probing with any external X-rays. We're simply measuring what's being emitted from the source. These are unclassified inspection objects. And this is just to show you on one of the systems we'll talk about. Their gamma spectra are in fact fairly close. The neutron spectra are in fact essentially overlapped. And these are labeled as IO8 and IO9. Idaho Inspection Object 8 and Idaho Inspection Object 9. There's about 12 or something of these type of objects. What's the system we're going to use? Well, this is a collaboration with Sandia National Labs, and they helped develop what's called a fast neutron-coated aperture imager. They developed it for some of these arms control applications. And let me just describe this system somewhat briefly. But you have a detector here. You have an aperture here. This is actually a neutron aperture, so it's essentially plastic, polyethylene. This system is a series of gamma cameras. Here's a picture of what one of them looks like. There's an array of 4 by 4 of them. Each of those has a scintillation crystal that is segmented into a 10 by 10 array of segmented crystals. So in actuality, when you generate an image, you generate a 40 by 40 image. So there's essentially 40 natural pixels to the left and right, up and down. As a gamma ray or a neutron enters this system, it interacts with the scintillation crystal, generates an event. You can use the signals to do pulse shape discrimination, so we can determine whether it was a gamma ray or a neutron that interacted. And we can also use that information to ID which crystal the interaction took place in. And this is a coded aperture system, although we're not doing any of the rotations in this problem. We're just using it as sort of a general system. So this is a system, as I said, developed by Sandia and Oak Ridge National Lab. This is the type of data that we get off that system. They can do conventional MLEM reconstruction and get nice reconstructions of a point source and a distributed source, and things do work quite well. We don't want to do that. In fact, we don't even want to generate this. Let me just mention that Chris developed these beautiful giant models of both the Idaho inspection objects and this imaging system, including all the complications of the mask here, the sort of class 19 coded aperture, all of the physics that go on in the cameras, the blurring, the energy blurring, the pulse shape discrimination, all that's included in these beautiful giant 4 models. And the first problem we had to deal with is how do we use imaging systems but not generate an image? And the answer to that is quite simple. And that is all of these systems that we're dealing with, and in fact, a lot of the systems I talked about previously in the adaptive problem, they're photon counting systems, and they're not integrating detectors. So when a gamma ray or a neutron interacts, it produces a signal. That signal is read off, and usually it's aggregated to generate an image, but it doesn't have to be aggregated. We could take that information, that list mode data, process it, and then throw it away. And so these are list mode systems, and that is every event that occurs generates an estimated energy, an estimated position, and an estimated particle type, whether it's a gamma ray or a neutron. And so what we're going to do is process or generate methods for processing events one by one and update a single number, which is a test statistic, which we'll use to threshold. So that test statistic is going to be used to essentially generate that red light, green light answer. And so there is no image formed. There's no data stored except for a single number, the test statistic. I have here a plot. We don't even generate that. We just keep track of the last value. Everything else is thrown away in the electronics. And so that accounts for this lower half of the chain. Before we had we didn't have list mode data. We had an image that's sensitive. So now we're not storing an image, so everything should be fine. What really happens, though, is to make decisions on list mode data, you shift a lot of the burden to this observer model. So now the observer model has a much more difficult challenge, and there's a lot of sensitive information in this observer model. I'm getting a little low on time here, so I'm going to move a little quickly. Let me just mention nuisance parameters. I talked a lot about object variability before. I'm going to essentially call the object variability here nuisance parameters. Nuisance parameters are key in any problem, and they're especially key in this problem. And that's shown very well by these graphs that Chris generated. This was, those Idaho inspection objects. They're cubic in nature. So if you generate calibration data and testing data for one orientation, things work great. You get perfect AUCs for low signal counts. When you rotate one of those objects 45 degrees, everything drops immediately to guessing. 0.5 is the guessing observer. Might as well flip a coin. But we know how to account for the nuisance parameters. Borrowing on work done by Luca Caiucci and Abhinav Jha and others, Eric Clarkson and Harry, on list mode observer models. We know how to account for these types of things and have done so. And the last thing I want to talk about here is how do we generate observer models that hide sensitive information. And this was a very nice demonstration that Chris did in the following task. So here's an XY plane. This is a toy problem, but you'll sort of understand what we're trying to do here in a second. So let's imagine we have 3 objects, object A, B, and C. And we want to distinguish whether the object is at location A or at location B. This looks like a long distance, but it's in millimeters here. It's 2 centimeters change. We are going to optimize the performance for distinguishing between A and B, optimize some observer model for distinguishing between A and B, but simultaneously minimize the performance between A and C. And the idea here is to treat, for example, X position as a sensitive parameter. Now, in reality, it's not a sensitive parameter, but let's pretend it is and see what happens. So Y information is insensitive. That's fine. You can share that with the monitor. X information is sensitive. No way you can share it. And he generated a metric that he optimized a linear observer for to, again, maximize the observer performance here, minimize it here. And sure enough, when you test what you trained it on, you get nice performance. Higher curves are better. Red is a very nice high curve. When you test it on what you tried to penalize, sure enough, you get a low performance. You get very poor performance when you on the thing you actually penalized. If I just look at two things the observer wasn't trained on, it wasn't trained to do this task, but it's a wide difference. You get very nice performance, shown in blue here. And when I test it on objects that have a smaller X separation, not the one it was trained on, you even get a worse performance. So I'm not showing the templates, but effectively what we've done is we've trained an observer that makes decisions using Y changes and is completely insensitive to X changes. So we can now design observer models to specifically hide sensitive information. And the hope is that this will allow this upper right box to turn green. We can have a model observer that doesn't store sensitive information. Okay, so I've gone a little over here. Let me just summarize this last project. We want to do imaging without images. List mode data solves that. Nuisance parameters are a key, and we want to. The really difficult challenge is to generate observer models that contain no sensitive information. Okay, so I've shown you three applications. Some of the things that me and people I work with have been working on: one clinical, one small animal, one homeland security. I just want to thank, of course, the sponsors, collaborators, and lots of students here. And open the floor for questions if people have questions.